All right, let's get started. Welcome, everybody. Welcome. So before I introduce today's speaker, let me remind you that during the seminar, once the speaker starts speaking, please put your microphones on mute. When you want to ask a question, please unmute yourself then and ask a question. So that's how it works. At the end of the talk, so there will be a period for sort of recorded questions, which go on the recorded portion of the talk. But after that, so once the recording stops, you don't have to disappear right away. We also have an extended period of informal discussion when you still are welcome to hang around. So that's a period which used to be called wine and cheese, which we are not able to provide at the moment. So it's sort of virtual wine and cheese, but you're welcome to stay and chat. So with that said, I'm pleased to welcome today's speaker. It's Arman Darbinyan from Texas A&M University, and he's going to tell us something about subgroups of left-orderable groups.
Thank you, Ilya. Thank you for inviting me. It's an honor to be in this famous group theory seminar. So let me start, and I'm going to talk about subgroups of left-orderable groups, and I will consider several perspectives of it. So mostly I will consider the subgroups of left-orderable simple groups, and I'll try to investigate and describe some connections between the subgroup and the large group itself. So let me start from the definition, reminding you the definition of left-orderable groups. So we say that the group G, and by the way, in this talk, I only consider countable groups. Most of the times it will be finitely generated groups, but sometimes not necessarily finitely generated, but countable. So we say that G is a left-orderable group with the given order. If this order is linear order, and in addition, we have this left invariance of the group multiplication, meaning that if G is smaller than H, then after multiplying G and H with an element X from the group G, this order still is being preserved. This definition is, of course, of combinatorial flavor. However, what is remarkable about the property of left-orderability is that one can find some alternative definitions that are of more algebraic flavor or even of topological flavor. So the second definition is of more algebraic accentuation. It says that the group is left-orderable if there exists semigroups that I denote by P minus and P plus, such that P minus is precisely composed of inverses of P plus. P minus and P plus are disjoint, and G is a union of the trivial element with P minus and P plus. Once we have this decomposition of the group G into semigroup, into the union of semigroups, then one can say that X is less than Y. One can define this order if and only if X inverse times Y belongs to the semigroup P plus. It's easy to see that this way we have a left order. On the other hand, once the left order is given according to the first definition, meaning explicitly, then one can define a positive cone, which will be composed of all the elements of the group G that are strictly larger than the trivial element. So this positive cone, defined this way, will serve as the semigroup P plus. So this is how these two definitions are related. Interesting and curious fact that already was mentioned in the previous seminar talk is that left-orderable groups, they satisfy unique product property, which implies on its own terms that they satisfy Kaplansky's unit conjecture. Here I would like to mention that an easy way to construct a group that doesn't carry any left order on it is groups with torsions. Once the group has a torsion, then it does not have any left order on it. It's an easy observation. However, if one who is not specialized, in this kind of topics, off top of the head will have some hard time to find a finitely generated group that doesn't contain torsions and at the same time is not left-orderable. This gives some idea why, previous wrong counterexamples to the Komplowski's conjecture, they appear to be that all have some hidden torsions in them. So now I want to go to the promised topological characterization of left-orderable groups. In fact, this characterization is for countable left-orderable groups. So here the cardinality really matters. This characterization says that the countable countable group is left-orderable if and only if it's a subgroup, or in other words, it embeds into the group of orientation preserving homeomorphisms of the real line. We know that every countable group embeds into homomorphism subgroup of the real line. However, here the important thing is that it also preserves the orientation. The proof of this fact is the most common and famous proof is by so-called dynamical realization, and the sketch of the proof is presented here, which is quite easy. It is basically composed of two steps. The first step is to construct a bijection between the group G and the set of rationals, so that this bijection preserves the order of the group, meaning that if element X of the group is less than element Y of the group G, then their images also preserve this order. So once you have these bijections, then this map actually gives you the embedding construction. So here is the map that I denote by rho phi. And it's quite easy to see that actually this satisfies all these group theoretical conditions to make it an embedding, and it also preserves the order. So once you have this map from going from the rationals to rationals, you can extend it, since it's order preserving, you can extend it to a map from the real numbers to the real numbers that will be continuous and will preserve the order. So this is called dynamical realization. So a curious fact is that, yes, I skipped this, this one. So the curious fact is that once we move to the cardinality that is continuum, then this fact is not true anymore. However, the result is not trivial. And it was obtained by Catherine Mann in 2015. Who constructed an example of a group of cardinality continuums that is not a subgroup of orientation preserving homomorphisms of the real line. So the next topic that I would like to discuss is a computability of left-order subgroups. In the most intuitive way, one can say that a given left order on the group, on the countable group G, is computable if there exists an algorithm that for any input element of the group G figures out which one of the three options takes place, whether it is larger than the trivial element, or it is equal to the trivial element, or it is smaller than the trivial element. So this is the informal definition, which is quite natural. In particular, once we have a computable left order on a finitely generated group, it implies immediately that the word problem is decidable. If we go to a little bit more formal definitions, then of course one has to differentiate the cases when the group is finitely generated and when it is not. Because when the group is not finitely generated, then the computability property is with respect to a certain enumeration of the group G, or a certain enumeration of the set of generators of the group G. So with respect to one enumeration, it can be computable, and with respect to another one, it can be not computable. However, we don't have this issue once we move to finitely generated groups, because in this case, one can rigorously define computability of left orders by considering so-called language of positive con. So assuming that the group G is generated by a finite set of generators X, then the language of the positive con will be a set of finite words formed by the generators of the group and their inverses, so that they represent strictly positive, or by positive I mean that it is strictly larger than the trivial element. So the definition is given here, and then the group will have the order on the group G will be computable if the language of the positive con is recursive. It might be that the language of the positive con is not recursive, however, it is recursively enumerable. So this is also possible, meaning that the word problem is not decidable, but one can detect the one can enlist the elements in the positive con. So what I like about this definition based on the language of the positive con is that here we can ask all the natural questions in the context of the formal languages that are possible to ask, in particular for the word problem in groups. So one can investigate regularity, for example, recursive enumerability, recursiveness, etc. So all these possible questions that exist, say, for example, for the word problem. The topic actually of studying systematically the computability of left orders in groups was initiated by logicians. And this is one reason why I give these definitions, not just for finitely generated groups, because in group theory, mostly once we consider this kind of questions, we are interested only in the case when the group is finitely generated. However, when we go into the logics, then this is not true anymore, because logicians are also interested in the groups that are not necessarily finitely generated. And this topic was started by Donny and Kurtz, who are famous logicians. I must say that still, like, there are many open questions in that. For example, one question that is very interesting for me is that can one characterize all the groups that are left orderable, and the left order is a regular language. So so we know that there is this famous results, for example, the theorem of Schub-Miller about the word problem. So this kind of theorems can, whether or not, can be extended for the language of the positive con. Still not much is known in that direction, and even some of the most basic questions, one of which was asking the following. So imagine that you have a group that is with decidable word problem, or it is computable when it is not finitely generated. It is also left orderable. So does there exist a special representation of the group for which the order becomes computable? So there was some evidence suggesting that it might be true. However, this recently, Harrison Trainer found an example of a group that is computable and left orderable. However, with respect to any presentation or enumeration of the group, it never has a computable left order. I must say that this result was later generalized, and in fact, not only countable group, but also there exists a finitely generated group, in fact, two generated left orderable or even bi-orderable group that has decidable word problem and left orderable, and it doesn't belong to any larger countable group with this with computable left order. So yeah. So the main question that I would like to touch in my talk is which groups embed into finitely generated simple left orderable groups, and what properties may such embeddings preserve. It's worthwhile to note that this topic is quite an old one, and if we skip the term simple or left orderable, from the statement of the question, then this question is already, it already has a rich history. For example, in 1960, Neumann showed that, in fact, any group that is countable and left-orderable is a subgroup of a finally generated left-orderable group. Here, just not a trivial observations that one cannot ask for more by this theorem of Neumann, in the sense that if a group is not left-orderable, then it never can be a subgroup of a left-orderable group. So left-orderability is preserved by considering the subgroups. A strengthening of the result of Neumann is by Bludov and Glass, who in 2009 showed that, in fact, one can construct a version of the famous Hikman embedding, which considers the class of left-orderable groups. So basically, it's the Hikman theorem, but restricted to the class of left-orderable groups. And when we omit the term left-orderable and only consider the simple groups in the question that is formulated above, then this is also well studied, and actually famous constructions by Filippo, by Gorushkin, by Shub, they show that actually any countable group is a subgroup of finitely generated simple group. Here I would like to also pay attention that these embedding constructions, they mostly were done by using either some risk product techniques. For example, the embedding constructions of Bernhard Neumann and Filippo, they were built on using risk product techniques, or they were using some free constructions like the construction of Gorushkin or Shub. Another result, embedding result, that in addition preserves some properties was given by Richard Thompson, who famously showed that every finitely generated group embeds into a finitely generated simple group, which in addition also preserves two properties. One is a property of more algebraic flavor that says that the embedding is a Frattini embedding, which means that the subgroup that is embedded into the large group, the small group that is embedded into the large group, it exhibits conjugacy rigidity property in the sense that if two elements of the subgroup are conjugate inside the large group, then they are also conjugate inside this initial group, which is denoted in my slide by H. Probably the most important property for Richard Thompson was that it, in addition, preserves the word problem. So this was the main motivation, actually, for Thompson to consider this embedding construction. However, probably this construction for mathematicians became famous because it was it was introducing the famous Thompson's groups, which nowadays probably one of the most famous groups, right? So, another embedding construction that also concentrates on additional properties was given by Brightson, who was considering a class of finitely generated groups that is closed under some amalgamation property, namely amalgamation by free subgroups. And he showed that if you have this class, then there will exist one finitely generated group in which all these groups will embed in a quasi-isometric way. So this embedding is, and this large group, which is important for us, because we'll later return to this theorem. So this large group actually has no proper subgroup of finite index. Here I would like to note that simple groups also have this property, but also free groups have this property. Not necessarily simple groups, but simple groups definitely have this property. And the properties that this embedding preserves is of more geometric flavor, because it basically shows some structural connections between the geometry of the initial group and the geometry of the final group. The geometry of the initial group in the final group is not too much distorted in a sense. So the most formal definition is by the length of the word problem, the word metric. So the word metrics of the initial group with respect to the generators of the large group is related to the word metric with respect to the generators of the initial group. So as I already mentioned, the Thompson's group is especially important in particular because of the method, but also because it preserves the word problem. And the reason why this was important, that the embedding of Thompson preserves the word problem, was the famous theorem. At that time, it was already a celebrated theorem of Boons and Hikman that was characterizing the finitely generated groups that have decidable word problem. Namely, the Boons and Hikman's theorem, which is actually a consequence of Hikman's famous embedding theorem. It says that the word problem is a group, finitely generated group G, is decidable if and only if G is a subgroup of a simple subgroup of a finitely presented group. So Thompson's theorem immediately implies that in this assertion of Boons and Hikman, one can take the simple subgroup to be finitely generated, which makes the statement of the theorem even more finitistic. So I already mentioned the result of Bludov and Glass. But Bludov and Glass also considered their Hikman embedding type result for left-orderable groups, also in the context of the Boons-Hikman theorem. In particular, they showed that the statement of Boons-Hikman theorem stays precisely the same once we move from the class of finitely generated groups to the class of finitely generated left-orderable groups. So in the assertion of Boons-Hikman theorem, one just needs to add the term left-orderability. And in this context, the natural question is the question that is formulated here. It says, can one take the simple subgroup to be finitely generated for the version of Boons-Hikman theorem for left-orderable groups? So basically, the motivation of the question is very natural, and this is precisely the type of strengthening. If the answer to the question is positive, then it will lead to the same strengthening as the theorem of Thompson led for Boons-Hikman theorem. This question was actually in a variant of this question was formulated by Glass in his book on left-orderable groups. So another object that is interesting in the context of the questions that I already mentioned is the objects, the groups that are at the same time finitely generated. They are left-orderable and they are simple. The existence of this type of groups actually was an old question for quite some time that is formulated by Rentula in 1980. And probably one of the important motivations to consider this question is the fact that once we move from left-orderable groups to the class of bi-orderable groups, which means that in addition, the order is preserved by the right action on the elements of the groups. So once we move to bi-orderable groups, then it's known that this type of groups don't exist, because bi-orderable groups, they are locally indicable. And it was in 2019 when Hyde and Lotta, they showed that the existence of finitely generated left-orderable simple groups. extending the ideas from the construction of Hyde and Lotta, soon Mattebon and Trestino, they developed, they constructed another example of such groups that is exhibiting a more explicit dynamical flavor. So the construction is based on more ideas that come from dynamics. They use some topological properties of some groups of homeomorphisms. But what is interesting about the example of Hyde and Lotta and Mattebon and Trestino is that in a very essential way, they are making use of piecewise linear groups. Just want to remind that one of the interpretations of Thompson's group is also by the terminology of piecewise linear groups. And the theorem here that I would like to announce and advertise is by me and Steenbok, that says that basically that gives some answer to the question formulated, which groups are subgroups of finitely generated simple left-orderable groups. It says that every countable left-orderable group G in fact embeds into a finitely generated left-orderable simple group H. So if you consider this first statement, then of course it cannot be made stronger in the sense that if a group is a subgroup of finitely generated left-orderable group, left-orderable simple groups, then it must be first of all countable, and second, it must be left-orderable. So one cannot hope any strengthening of this statement. However, one might be interested in considering what other properties such embeddings can preserve, just in the spirit of some of the previous embedding theorems that I mentioned. And here we obtain some properties that such embeddings can preserve. First of all, these embeddings, like in the case of the embedding of Thompson, can be made to be Frattini embeddings. Second, if the order of the group G is computable, or in other words, this was even not very precise statement when I said the order of the group G is computable in the following sense. Probably it's worthwhile to mention that there exists this theorem which is called Lineal's dichotomy theorem. And Lineal's dichotomy theorem says a group, a countable group has either finite number of left orders, could be 0 or just any finite other number, or it can have uncountable number of left orders. So this means that since there might be uncountable number of left orders on the group G, it might be that some of the left orders are computable and some of them are not computable. So that's why the more precise statement would be that G has a computable left order, meaning that not necessarily all of the left orders are computable. So if G has these properties, and so does H. And the third property that we consider is in the spirit of the theorem of Wrightson that says that G is finitely generated. If G is finitely generated, then the embedding is isometric. So I need to make a short remark what I mean by isometric embedding. But even before that, I would like to make another remark stating that if we skip the term left-orderability from the statement of this theorem, then it still stays true, meaning that the first statement stays true, and also the the additional properties of being Frattini embedding and being isometric will still be preserved. Now, a short remark what I mean by isometric embedding. Well, I need to go to the previous slide. So here I give a definition of quasi-isometric embedding. And if there exists some particular finite generating sets, X and Y, with respect to which this constant C1 and C2 can be taken to be equal to 1, then this embedding we call isometric embedding. So it gives like a more precise structure, the relationship of the structure of geometries of the initial and final group. And one corollary that we have from the previous theorem is in fact the partial answer for the aforementioned question of gloss. The theorem says that the finitely generated group that has a recursively enumerable left order has decidable word problem if and only if it is a subgroup of finitely generated simple subgroup of finitely presented left orderable group. Basically, it says that for the class of groups that have a recursively enumerable left orderable group, one can make this strengthening of the Boon-Hikman type theorem for left orderable groups. And another immediate corollary from the main theorem would be a strengthening of the statement of the Brightson theorem, because in this case, we can take the final group, not just the groups that doesn't possess any proper finite quotients, but we can just take it to be a simple group. And I would like to mention that this theorem was recently independently also obtained by Belk and Zaremsky. And their construction also uses some generalizations of piecewise linear groups, which is also true for our constructions. So remarkably, piecewise linear groups, they are a very useful tool in obtaining this type of results. And here, I would like to give a very rough scheme of the embedding constructions that we have. So as you noticed, we start, the statement of the embedding theorem is for any countable group, not necessarily finitely generated. However, it's not easy to work with just countable groups when especially you want to preserve some, when you consider some embeddings, and especially you want to preserve some computability and other properties. So this is the reason why this embedding construction has several steps. So in the first step of the construction, one has to embed the group G in a group G1 that preserves this left order, but also so that the group G1 is finitely generated. So that with finitely generated groups, it's easier to work. And of course, this embedding should be in a smart way so that it preserves some additional conditions like Fratini, etc., like computability properties, etc. Once you have the this embedding into the group G1, then the next step is to embed the group G1 into another finitely generated group G2, but this time the group G2 must be also, in addition of being left orderable, it should be also perfect group. Just want to remind you what is perfect group. Perfect group means that the group coincides with its derived subgroup. In particular, all the non-abelian, non-trivial, I would say, non-trivial simple groups, they are perfect groups. In this direction, I would like to mention the theorem of Bergman, which was before the theorem of Hyde and Lotta, and it was about the existence of perfect left orderable groups. And the motivation of Bergman was exactly to construct left orderable groups that are not locally indicable. So one can consider this embedding into the group G2 as a strengthening of the theorem of Bergman. And of course, these embeddings preserve this Frattini and quasi-isometry. So they preserve some additional properties in order to make the statement of my theorem, the theorems that I stated true. And finally, once one has this embedding into the group G2, then the final step is to embed already into the into a finally generated simple left-orderable group. Here, I would like to mention that the group H is a subgroup of the group of homomorphisms of a mapping torus, to which I will return a little bit later. But before that, since there might be a question why we need this intermediate step into embedding into a perfect group, of embedding into perfect group, the reason is that at some point, in order to show this simplicity of the final group H, we will apply the criterion of Epstein. It's a variation of the criterion of Epstein that is given here. It's a little bit technical, so not a very difficult statement, and very famous criterion for proving simplicity of various groups. So in particular, it considers rigid stabilizer and says, so the idea is that the rigid stabilizer of some subset of a set on which the group G acts would be precisely the elements of the groups that are being fixed for outside of the stabilizer, outside of U. So and the idea is that once you have the group is perfect, then if the rigid stabilizer coincides with the whole group, then the criteria of Epstein states that this rigid stabilizer, which in some particular cases will coincide with the derived subgroup of the group, it will belong to a normal subgroup of the group that we are considering, some hypothetical normal subgroup. And since the group is perfect, this derived subgroup of the group that is contained in the normal group can be true only when this normal group N, normal subgroup N, it coincides with the whole group. So the way of applying this a little bit technical, but it just gives some idea why we need this intermediate step.
I have a question about the theorem. So who is H here?
Who is what?
Who is H in the theorem?
Yes, so in the theorem of Epstein, right?
Yes, yes.
That's a good point. Actually, it would be more precise if I used the notation instead of GH.
So G is the same as H here, or?
Yes, so there is a typo. There is a typo in the statement because in both of the places I was supposed to use H.
Okay.
It looks confusing, but yeah, it's just a typo. So in order to go to the step 3 of constructing the group H, in a very essential way, we use the aforementioned construction of Mattebon and Tristino. And here I would like to go back and provide a little bit more details about this construction, because it's a novel construction and actually exhibits very beautiful mathematical sites on it. So first I would like to start from some setup. By the way, this setup is a little bit simplified, because in the paper of Mattebon and Tristino, they consider a more general situation. However, for our purpose, it's enough to consider a little bit more simplified setup. So let A be the set of bi-infinite sequences consisting of zeros and ones. So it's bi-infinite words of zeros and ones. And let's consider phi, which is a right shift on the sequences. It just moves by right. So it acts by shifting to right. And let's consider the subset, infinite subset of A, so that the couple, the pair, x phi will be an infinite minimal subshift. By minimal subshift, I mean that, first of all, if phi acts on the elements of x, then it moves to another element that still belongs to x. So x is closed by the right shifts. And in addition, there does not exist any a proper subset of the set X with respect to which will be also invariant under the right shift. So this is the second thing to consider. And of course, once we consider it, it's natural to pair it with topology. In this case, it will be the product topology. So once you have this, the next step, which is already a particular case of mapping tori, this sigma, which will be a quotient space of the Cartesian product of x and the space of real numbers. So this particular quotient is with respect to an equivalence relationship that is defined here. So basically, you are shifting x by one move, and you are shifting t, which is the second coordinate of the xr of an element from this Cartesian product, and you are shifting t also by one. So if you have these unit shifts of both of the coordinates, then these elements are defined to be equivalent. Then you are taking the quotient of the space, by that obtaining mapping torus. And then the groups that Mattebon and Tristina constructed actually is a group of homomorphisms of this mapping torus. I would like to give a little bit more details about how this group is constructed, because first of all, it's very beautiful. So for that, I want to open a OneNote. So can you see my OneNote? Or is it still showing the slides?
Slides.
Okay, you can see. That's good. Oh, still slides, you said?
Yes,
Okay.
we only see the slides, so there is nothing
Yeah,
else.
I don't know how to move from the slides to this thing. Maybe I should stop sharing, or who can help me? Okay, I think I figured out what to do. Sorry for that. I don't have much experience with using the technologies, but it seems that now it shows the OneNote, right?
Yes, now it's there.
Perfect, thank you. So, since it's a Cartesian product of x with r, I just visualize it by drawing this xr coordinate system. So it's it's an informal picture. You can just consider it as an abstraction, and then consider this rectangle, this blue rectangle in the xr coordinate system. So this rectangle, when it's projected to the x-axis, then it is Kloppen. And when it is projected to the r-axis, then it's an interval of length strictly less than 1. Then the idea is to consider homomorphisms on the mapping torus, which will be induced by homomorphisms of this Cartesian product XR that actually make deformations only inside this rectangle. Namely, if you consider these green lines, these vertical green lines, which are some parts of the fibers that go in from X. So the idea is to consider them as intervals on which the elements of Thompson's group T act. Actually F, Thompson's group F act. So you take just any element from the Thompson's group F, and just recall that these elements of the Thompson's group, they can be interpreted as piecewise linear actions on unit interval, so that they have finitely many breaking points. These points are dyadic points, and the slopes are powers of 2. So, and let's act on each of these fiber by a fixed element of the Thompson's group F. So what happens is that if a particular element of Thompson's group act, it brings this element to some other elements on the same part of the fiber. It brings the corresponding element from the corresponding point from another fiber to, again, corresponding point on the same fiber. So this way, actually, we define a homomorphism on the XR space because these elements that are on this boundary, they are being fixed. They are not moving. And the fact that it is Kloppen is precisely to make sure that this will be homomorphisms. So now consider the induced homomorphism, that is by this homomorphism on XR plane on the mapping tori. So this rectangle, blue rectangle, will go to some other rectangle on the mapping tori. So everything here is twisted, so the fibers have, you know, some twisted spiral shape. However, it will induce actually this way it will go. It will induce a homomorphism of sigma. So now we are almost done with the definition of Mattebon-Tristino's group. Now consider all these type of transformations with respect to all possible dyadic charts. Namely, you can take this chart, you can take actually this type of infinite chart. It's also dyadic. The important thing is that this should be less than, the width should be less than 1. So consider all these charts and consider all these homomorphisms that are with respect to these charts. This group of homomorphisms that is generated by these homomorphisms, it's called it's denoted by T phi in the paper of Mattebon and Tristino. And the remarkable theorem of Mattebon and Tristino states that T phi is finitely generated, it is simple, and it is left-orderable. So this is pretty much the construction. I skipped, of course, some technical details about how to prove these properties for T phi. But in general, the insight is deep. However, the proofs are not very, very complex. Now I want to go back to the slide. And this is the theorems that I just mentioned. And one more technical thing that, so actually we need 2 more technical things in order to complete our theorem. One is that we need to develop some chart representations for homomorphisms, particular homomorphisms that act, that are on this mapping tori. But in addition, in order to preserve these properties, we have to modify the dynamical realization or this topological characterization of left-orderable groups that I mentioned. So here is the technical theorem that is of key importance to construct embeddings that preserve, in addition, these extra properties of being quasi-isometric, of being Fratini, and preserving computability properties. So since I'm now out of time, it's a good point to finish.
No, actually, you're not.
Oh, okay. So how much time do I have?
You have until 5 o'clock, so you have plenty of time.
Oh, okay.
Yes.
Well, yeah, I was almost proud of myself for computing my time so well, but okay. So I can stop on this slide a little bit more and make some comments. So first of all, we introduce what is dyadic part, sorry, of a rational number. So each rational number has the presentation where you just separate the part that is a power of 2 from the part that is quotient of odd numbers. And this power of 2, the exponent of the power of 2, is what we call dyadic part of the rational number. Then we have this concept of strongly permuting dyadic parts. The statement is a little bit technical, though not too much. It's of some combinatorial flavor, I would say. So it says that, well, if you have G that is a bijection between Q sub I and Q sub J, here I would like to say Q sub I is the set of rational numbers on the interval I, and correspondingly we define Q sub J. Then this bijection will be strongly will strongly permute dyadic parts if these two properties take place. So for each m that is an integer, there exists at most one element from the range of G, such that the dyadic part of X is equal to the given m, and in addition, the dyadic part of its image is non-positive. And the second property that it must preserve is that for two different elements in the range of Qi, if their dyadic parts coincide, then their images will have diverging non-equal dyadic parts. So once you have this, then this property is what we call strongly permuting dyadic part, and the technical lemmas that plays a key role in our construction is that actually one can modify this topological characterization of countable left-orderable groups by saying that a left-orderable group is a countable group is left-orderable even only if the group can be embedded into the orientation preserving homomorphisms of some interval G. Here in the statement I didn't mention what is G, but G is just some any closed interval. Let's consider closed unit interval, such that for all elements G, if we consider the homomorphism of the unit interval J that corresponds to the element G, then it will have this property of strongly permuting dyadic parts. So even though I will not go too much into, and also, yes, so this embedding will also preserve the computability properties of the initial group G. And by computability in particular, I mean that if you consider the image of the group G into the group of homomorphisms of the unit interval, then this image will consist of computable homomorphisms. So here I have to define what I mean by computable homomorphisms of the unit interval. I mean the following. The rational points will go to rational points. That's the first statement. And the second statement that the restriction of the homomorphism to the rational point will be computable in the standard sense. So this is what I mean by saying that the image of G will be composed of computable elements. So if I have like a few more minutes, I would like to make another remark, is that in fact, the first statement of the theorem that I mentioned, so I want to go to this theorem, the first statement is much easier to prove modulo the first two steps in this embedding scheme, and modulo the construction of Mattebon and Tristino. Because the main difficulties appear once you try to, preserve some geometric properties to control the geometry of the final group H. In order to control, we need some rigidity structure, some rigid structure. And this is precisely why we introduced these strong dyadical permutations. However, one can also modify this construction. This is a very flexible construction. One can modify it also to, for example, reprove the theorem of Thomson that I mentioned. In fact, it's quite subtle to see, but many ideas that Thomson had in his original paper, they're of very, very heavy combinatorial flavor. But if you move from this combinatorial perspective to dynamical perspective, then actually our construction has lots of similarities with the construction of Thomson's, though it's different constructions, but still there are some parallels, definite parallels between them. So one can move also to reprove this theorem, but this will consider some other homomorphism groups involved. So there is some work to be done. So what I mean is that this construction is quite flexible and it can be modified in different ways to produce some other nice examples of embeddings and maybe also some nice examples of groups with unexpected properties. So let me also go to my final slide and say thank you to you.
All right. Okay, thank you very much. Let's thank Arman. Okay, thank you. And now, if there are any questions to the speaker, you are welcome to unmute yourselves and ask them, please.
Can you say something about the preservation of the word problem, like decidability?
Yes. So that's a good point, because in our theorem, we have the following. So we have that it preserves the computability. Mm-hmm. And it's quite technical to show that it preserves the computability. But the idea is that I need to go to the slide, to this OneNote slide. So just let me share it. So the idea is that we consider some extra homeomorphisms on this space in order to embed the group G2 into H. And for example, assumes that we add some, and by the way, yeah, all the homeomorphisms that we consider, that they have finite chart representations in the following sense. It means that all these homeomorphisms, they are composed by homeomorphisms on dyadic charts, and there is only finitely many. So a homeomorphism can act simultaneously on this chart, on this chart, and on this chart. So, but the group of homeomorphisms of Mattebon and Tristino, in fact, he lives in the group H that we construct. So there is a major problem. How to make sure that the interaction between the elements of Mattei-Bon-Tristino group with the additional homomorphisms, first of all, it preserves some geometry, and second, it preserves the computability properties. It is not an easy task because this interaction should keep some structure. We need to be able to control this structure. And this is the main technical issues that we try to overcome. But I would like to mention that we still don't know how to construct this embedding that will preserve not just the computability of the left order, but will preserve just the word problem. Because there is much more structure that has to be preserved in order to make sure that the word problem is preserved, despite of the fact the group has computable left order or not. The reason why computable left order is helpful for us, because once the left order is computable by the aforementioned modification of this dynamical realization, you can represent the elements of the group, left-orderable group, into homomorphisms of the unit interval that will be computable maps. We don't know how to do that when only decidability of the word problem is known. However, we know how to modify the construction that will preserve only the word problem with the cost of left orderability. So we can skip left orderability, but preserve the word problem. Unfortunately, everything has its cost. So you preserve the word problem, you skip either simplicity or left orderability, or you just neglect the preservation of a word problem.
I see. Thank you.
All right. Are there any other questions? Okay, let us thank Arman again. Thank you. Okay, so I'll stop the recording now. So,